So now that we understood how an oscillator works, now let's try to do something further than this. So the idea is that we want to arrive to a condition in which we can describe how we can do computation. So we are building all the fundamental elements of a CPU. So we found a way of creating a clock oscillator. We studied combinational circuits, and now we need to study this circuit which has this funny name. It's called flip-flop or latch also. Okay, so let's see. So now we have two NOR gates connected with this strange crossed feedback here, and the truth table we are going to study. So first, let's summarize here the behavior of a NOR gate. Sorry. So the NOR gate is the negation of an OR gate. The OR gate was the one for which all possible conditions but this, the first one, produced a 1, the other one was producing a 0, and so therefore a NOT gate at the output of an OR gate will produce this truth table. So in order to have a 1 for an OR gate, we have to have a 0 and another 0 here. All the other possibility gives a 0. So with this in mind, let's analyze this circuit starting from a condition. Let's say from this one. So here in red I highlighted the 1 logic value, and where you see black it means 0. So let's assume that, for instance, we have this output to be 1. So then this value is propagated back here, and we have a 1 at one input of this NOR gate. So if we go to the truth table and we say, for instance, that this red line corresponds to the A input, so if we have a A input to be equal to 1, no matter what's B, the output is 0. So it means that here we have 0, no matter what's the other value of the other input. So if this is 0, we are here, and if this is 0 and this other input is 0, the truth table is saying that we have a 1 here, which is this red line. So this situation is consistent with what is represented here with colors. One input is called set, the other one is called reset. So from this situation, let's try to reset the system. So I put a 1 at the reset input. So let's see what happens. So if I have a 1 at the reset, let's call this input A. Again, no matter what's in B, the output of this gate should be 0 according to the truth table. So this is 0 and this is 0. So 0 and 0 makes a 1. Here we have a 1 that goes here. So from this condition, by resetting this device, the output, which is called Q, went from 1 to 0. Now we go into this condition. We deactivate this is called reset condition. Now we analyze the set condition, so the condition for which the reset is deactivated and the set is 1. So again, if the set is 1, so if one input is 1, no matter the other, the output is 0. and here we have a 0, and then 0 and a 0 makes 1, which is 1 here at the output. So from this condition, now we have that the set input produced a 1 at the output. Now finally we can start from this, and we go back again to this other condition. So what happens now if once we reach this situation, we don't touch the reset, but we release the input? So from this condition, Q was at 1, we already analyzed this from the very beginning. And if Q was at 1, at the beginning there was an if. Now we produce this situation here with the set condition. So if we are in this situation and we change the input, the set input from 1 to 0, then the Q state at the output remains the same. So this situation is called hold. So what we have done so far, we created the simplest form of memory. So we activate one input. So from the point of view, let's say, of the behavior, it's like as we said to this guy, hey, there is an input at your S pin, your S terminal. I activate your input, and the guy says, okay, thanks, I will remember this information you gave me. And then if you are not giving this information again, so you're not saying this anymore, then the circuit will remember this forever until you reset it. And then you can start the memorization of a new information. Like you can tell the circuit again, hey, I activated your input again. Okay, thanks. Then you don't say this again, but the circuit will remember, and so on. So it's a very simple memory. There is one case which is called, in this context, the forbidden case. So if you activate both inputs at 1, this situation creates something that we don't want. So it creates an output for which this output Q and this complementary output Q negate are not anymore complementary. We can avoid to stimulate the input of this system with this configuration here, in order to avoid this, let's say, non-logic condition, something similar to this. So how can we do this? We do this with this type of circuit.